Hi all. In the previous video you have seen that how to install the pyTANSPEC package. In this video you are going to see how to use the package to reduce the TANSPEC data. So I'm keeping the data directory in this demo directory. This is my data directory. If we just check the list of files, so these are all the frames I have observed. So we can keep all the frames in the same directory. That will be convenient. Now we need to get the config file. For that we just go to the GitHub page of the package. Then we need to check out this generalized pipeline branch, this specific branch. Then we need to go to this directory, this pyTANSPEC. In the config directory we have the config file. You can just download this. Now I have downloaded it. Now I can open it. So you can see it is downloaded. Now I can open it in the favorite text editor you like. Mine is Emacs, so I'm just opening it in Emacs. Since I'm reducing an XD file, I can just keep this and this as FX. XD means the high resolution mode or cross-dispersed mode. So as you know, TANSPEC have low resolution, high resolution mode. So in this demonstration, I am reducing the high resolution mode spectrum. And if you want to change the seeing profile, the aperture window, you can change that here. So since my aperture window is -9 to 9, so I'm keeping as it is. If you want to change, you can change this. Maybe for now I'm just keeping it to -10 to 10, and the background window I'm keeping it to -15 to 15. Yeah, this we can specifically check and make the required change. So that's how we make the changes in the config file. Now we can run this pyTANSPEC pack. So let's go back to the directory and run pyspec, then the config file name, and we press enter. It will start running. It's asking hit enter to continue. We just hit enter, and we need to enter the number we need to number of the task. So first we need to run the 0th task, which will create the log file. So I'm entering that. So you can enter more than one task at a time, but for now I'm entering only one this time. So here it will ask for the data directory. Since the default one is shown here, I'm just entering that, or I can just press enter now. So yeah, that is done. We can open the text editor, go to the data directory which it is saved. So this is the log file. You can see that this ops log of images.txt, that is the name of the log file. I'm just opening this, and because I want to see each line completely instead of this view. So I'm running this toggle target lines once again. Yeah, now we can see better. So yeah, these are the list of all the data in that directory. So it have this continuum, sky, all the frames I have taken. These are the frames I want to reduce right now, this S0.5 frame. So we need to note down the F file number, that is 117, 118, 119. These numbers, these are the F number. So now let's go back to terminal and run the first task. Enter to continue. Now press Y and press 1 since we want to run the first task, which is to select the frame. Yeah, that is default. That's data directory is default. Here we need to enter the regular expression of the science frame. Here the typical name of our science frame is SD37725XDS0.5. That is the common thing in the file name. So I can just copy this part and just pasting it this here and putting a dot star and in the beginning and end. Then just press enter. Then it was taken. Now we need to enter the regular expression for continuum flat. So since it's an XD mode, we need to use the continuum for XD mode. So let's see which is the continuum frames available for XD mode. These are for LR mode. Yeah, these are available for XD mode. And if possible, use the same continuum used for the same slit. Since I'm extracting the spectrum taken with the slit 0.5, which having width 0.5 arc second, I am using the flat taken with the same slit. So that is here. I am just taking the regular expression of that, copying it, dot star, pasting it, dot star. Here we need to enter the file number also. So it is starting at 318, then ending at 322. We need to enter that here. So it's starting at 318, then ending at 322. That was taken. Now we need to enter the same thing, regular expression and file number for argon lamp we need to use. So here you need to keep in mind that when you do the observation, you should take lamps with that. So we can, then only the wavelength calibration will be correct. So we here we have taken a lot of lamps. You can see that a lot of argon lamps are here. So we need to check which one will work for us, which one we need to use for this specific data. So you have seen that there is a file number with the spectrum we have taken for target SD37725. That is the frame name. So you have seen that there is 117, 118, 119, 1120. Those are the file names. And there is 121, 122. 122 is for S 4.0, so till 121. So I took the lamps with this observation. So the file number of that will be near to that. So let's check that. When we go through the list of argon lamp, argon, and it should be for XD mode. Yeah, we found that there is these argon files which have file number 108109110. Also I have entered these things in the log notes when I took the observation. So I can say that these are the frames lamp frames I took with the observation. So that's important thing you should do while doing the observation. So I'm just copying the regular expression for this, pasting it here, and entering the file number. It's starting at 108 and ending at 110. So we can enter that here, 108 110. And we do the same thing for neon lamp. So we need to find the neon frames from this list. Neon XT. Since the argon ended at 110, neon must be starting at 111. Let's search for that maybe. Then it got something like this. Neon lamp XP 0.5. Neon XT. Here we found that 111, 112, 113. Those are the neon frames we need to. Others are neon frames, but those frames were not taken with this specific observation. So we cannot use that for this one, because when we do observations of different target, we may change the slit position. When even we put back the slit position, it may not come back to the exact same position, so that may cause errors in the wavelength calibration. So it is important to take lamps with the your science frame. So either you take the lamps before your science observation or after you after your observation. So just put the cal mirror in, then you should take the lamps, both argon and neon lamps. So here I am just copying the regular expression here. Then the file numbers are 111, 112 and 113. I am entering that here. 111, 112, 113, and just press enter. So these are the signs and the corresponding flat we need to use. So this will be shown for each science frame. So since I don't want to make any change, I am just closing this. If you want to make any change in this, you can make changes and close and just save it. Earlier one was for flat. This one is for lamps, for argon and neon corresponding to each science frame. Here also I don't want to make any change, so I'm just closing it. So that's all with task 1. Now I can run task 2, which is the manual um, inspection of science frame. So just repeat the process. There list 2. So this is this is the first science frame with 117. So here, yeah, I can use this frame. Just close this window, and since I want to accept this, I'm pressing AA. If you want to reject, you don't want to include this frame into the in the extraction process, you can press R. But here I want to use this, so just press AA. This one also I want to use, so press AA. This one also I want to use AA. If you can actually accept everything in one entry, just enter instead of that AA, you can just enter accept all. But I'm just entering one by one. Just close it AA, then close it AA. That's it. Now you can just press enter. Then it will show the list. If you want to exclude any frame, you can do that here. Also, if you want to separate any set, um, maybe if you have a dither frames, you can do the separation. You can just add a space here. It's just like that. Then this will be one set, this will be another set, and the extraction will be done like that. Since I don't want to make any such change, I am just keeping as it is and saving it, then just closing this window. So that's all in the task 2. In task 3 is to manually inspect the flats and lamps. So we can enter the list 3. Default thing is here. So this is a continuum flat. I want to include this. Just press A. Here also you can enter accept all. Then you can just accept all the frames. But I am just doing it one by one. A. Here the flat setting is already done. Now it is opening the lamp. This is the argon lamp frame. This is the argon spectrum. Here also just need to close this. Press A. Press A. Argon plus AA. This is neon frame. You can see the difference. So this also I want to use. So just close it. Press AA. Close it. AA. Close it. Press AA. So that is done. Now it is combining the just combine the argon and neon frame separately, then saved the result directory. The results are getting saved in the directory which is known as my TANSPEC reduction, because that was the name I given in the config file. So these are the the files that was created yet. So to run task 4, which is the flat correction, Just rerun it. Task 4. Now this will take a while. So now what's happening is it will take the flat frame and smoothen it out. So flat is basically just correcting for the pixel to pixel correction, basically quantum efficiency of each pixel. The flat correction is to do that. It will normalize the flat frame, then divide the science frame with the flats. So that is what is happening in this task. So creation of the normalized flat frame is what is taking some time. Also it will do cosmic ray correction, so that will take a while. Yeah, now that task is done. Now we can run task 5. Just press Y, enter 5. Here we can enter the name of the final spectrum, final extracted spectrum. Here I'm entering HD 37725 XD S0.5. So those are the information I want. Maybe, yeah, that's it. That's it. Made that. And this is the combined frame. I just need to since this looks fine, so I can just close this, and I don't have any dither frames, so I'm just pressing enter here. Just entering A here, then press enter. So yeah, task 5 is also done. Now we are going to the main task, which is the spectral extraction. Let's see, can we actually do the extraction? Same as before, plus 6 here. It's working on the extraction. Seems like it fitted the spectrum. Let's see the next frame. Yeah, you can see that the blue one is the trace. So it traced the aperture properly, and this bright thing is the our star spectrum. I just zoomed into that, and these are our background. Maybe I can just use a brighter background, but yeah, just for a demonstration I'm just showing this. Yeah, it fitted all, it could correctly trace all the apertures that you can see here. You can zoom in each of this and inspect manually. Yeah, since I'm satisfied with this extraction, I'm just closing it. These are the just concatenated all the orders. So TANSPEC have all 10 have 10 orders. This XD mode have 10 orders. That's what we are seeing here. I'm just closing this. Then it will run the wavelength calibration. So the wavelength calibration is also done, and it is saved as this with this extension .ms.wlc.fits. Let's see what is in that one. For that I'm using the command fitsinfo, and just pasting this thing here. You can see that in the primary one, that is the flux. First one, that is background flux 1, background flux 2, that is the background from above and below, and the third extension is the variance, and variance for background variance. There are two backgrounds, and those are shown here, and the wavelength array. So that those are the things saved, and we can see that in the directory also. So here you have seen another file with the name wlc.final.fits. Basically, what is that? Let's check what is that. Let's go to the directory, then let's just plot both of these. Okay, sorry, IPython is not installed in this. You can just quickly install it. Then I'm opening IPython from this machine memory .io import fits. So the first file is this one. Let's see, first let's see what is inside this one. Now let's take the flux. 1 equal to fish dot get data extension equal to 0, and the wavelength 1 equal to fish dot get data file 1, and the extension for wavelength is 6. Extension equal to 6. Let's plot that. 1 dot t plus 1 dot t, and that will do the job. plt dot show it didn't show anything basically. Yeah, this worked. So you can see that there is a spike here, and that is the background. You can see a lot of spikes here. Usually some stars don't have such spikes. So that is the sky background. We need to subtract that out, and this dot final dot fits have that subtracted. So let's see how the extension of that things are there. Let's check the file name. This thing is there, so just take fits info and the fits info of this thing. We can see it have only 3 extensions. The other one had 6 extensions. It had only 3 extensions: the flux, variance, and the wavelength. And the error is also propagated. So let's go back to IPython. Then I'm just calling this one. Flux 2 equal to fetch dot get data file 2. Yeah, by default the 0th extension will be taken, and the wavelength 2 equal to fetch dot get data file 2, and the extension here is 2, and I am making another figure. plt dot plot, need to change the names. Now you can see that there is no such spikes because we have subtracted the background. So that is what happened here, and that is there in the file with the extension wlc.final.fits, and that's the one you can use. And we are left with one more task, and that is the flux calibration. Now let's get out of the IPython. Let's run the pyTANSPEC once again. Press yes. So you can see that we have finished the task 0 to 6. Now enter the task 7, and that is for flux calibration, and that is also done. And we can just plot this. We need matplotlib, we need fits astropy.im.fits, and file name equal to, I can just use this as file name, and flux equal to fits dot get data and the wavelength is in which extension, that we can check. Wavelength is in second extension, that we can use here. Yeah, now what you are seeing is the Flux calibrated spectrum. Yeah, that's it. That's how the pyTANSPEC package works. Now you can use this for spectral extraction. Thank you for listening.